Type 2 hypersensitivity. This too is an antibody-mediated hypersensitive reaction. However, this is not restricted only to IgE. One can have IgM, IgG related immune complexes that are formed on target cells, and those give rise to an immune reaction that goes overboard. So let us look at the learning outcomes of this session. So type 2 hypersensitive reactions comprise antibody-mediated destruction of cells. Cytotoxic cells, through their Fc receptors, can bind to antibodies that in turn are bound to target cells. Now, this binding of the cytotoxic cells to these antibodies promote killing of the target cell. One of the best examples of type 2 hypersensitivity is that of ABO incompatibility, which is observed during blood transfusion, if the matching of the blood groups are not carried out. Rh incompatibility or hemolytic disease of the newborn is also a manifestation of type 2 hypersensitivity. Now, what one understands by an immune reaction in type 2 hypersensitivity is because of two main ways. One is that the tissue destruction can be complement mediated, and the other is that it can be through antibody dependent cell cytotoxicity. So when you look at when you look at a particular tissue in which the antibodies have come and associated with, then this immune complex that is formed between the antibody and the cells gives rise to a response such that you have polymorphonuclear cells coming towards the immune complex, and this itself is initiated by the anaphylatoxin. So based on the complement system, because you have these anaphylatoxins recruiting neutrophils towards the cells that have been bound to by the antibodies, it is these neutrophils then finally which would kind of destroy the cells by various means. Of course, what you have is platelet aggregation that happens. What happens is that you have certain malformations that can be formed due to the immune complex being formed on the blood vessels. Then you can also have vasoactive mediators that are released, and that gives rise to kinin forming enzymes and reactive oxygen species, and thereby this would help in killing the target cell. So as you can see, the immune cell or the cytotoxic cell has an Fc receptor, and this Fc receptor can bind to the antibody, and the antibody in turn is bound to the cells. So this is how complement mediated tissue destruction occurs. The other process, which is antibody dependent cell cytotoxicity, is such that the target cell with its epitopes would be bound to the antibody. Now, when you have the antibody bound to the target cell, then this is what is the immune complex that is formed. So these antibodies can be recognized by Fc receptors, say present on the natural killer cells. So the binding of the Fc receptor to the antibody leads to what is called as antibody dependent cell cytotoxicity, because a signal is transduced within, because of which the NK cell releases perforins and granzymes, and the perforins are able to make holes or make the membrane of the target cell more permeable, and the granzymes enter, and these granzymes then lead to lysis or the destruction of the cell per se. So these are the two major ways by which type 2 antibody mediated hypersensitivity takes place. Now, the best example, as we had mentioned, is the ABO incompatibility. So we all know that RBCs on its surface has several surface proteins. Some of them are glycoproteins, and these glycoproteins are responsible for defining the blood groups. So for example, the RBCs have what is called as the H antigen. So the H antigen is actually the precursor on which sugars get assembled to form what is called as blood group A, blood group B, and blood group O. So it is just the defined sugar moieties on the H antigens that determine whether the blood group is that of A, B, or O. Similarly, you have Mn blood group, you have Rh factor, which can be present, you have the KID factor, the Duffy factor, all of these are surface proteins that determine the blood groups on the, or that determine certain antigenicity, or rather the RBCs have a certain level of antigenicity because of the presence of these surface molecules. Now, when you look at O antigen, as we mentioned, the O antigen is formed on the H antigen per se, and what is formed is what is assembled is a group of all sugars forming what is called as the oligosaccharide, but then it has very typical sugars. So, for example, you have the fucose over here and you have two galactose present over here. This is the N-acetyl galactosamine. So, when you have this, then that is the O antigen. Now, suppose you have an extra N-acetyl galactosamine present, then that becomes the A antigen. And suppose you have, instead of N-acetyl galactosamine, a galactose being present, then that becomes the B antigen. So you can see H antigen is common in all of them, but other than that, the O itself is also part of every blood group, but the addition of extra sugars or added sugars and the type of the sugar that is added decides whether it is going to be A antigen, whether it is going to be B antigen. Now, we all know that if you have a person having a genotype of AA or AO, then the person will have the blood group A, and they would therefore have the antigens for A. But these people would have antibodies against B. Now, same goes for the blood group B. If they have the blood group B, then their antigen will be B and their isohemagglutinin will be anti-A. For those who have a blood group A and B, since they have both the antigens present, okay, they would not have an antibody formed against it, or they will not form an antibody against any of these because this is considered to be self for the AB blood group. Those who have blood group O, they have no antigen per se. So when we say no antigen, the H antigen is there, but there is no sugar moieties or oligosaccharide moiety present, and hence they are not antigens, and therefore in those people who have blood group O, you would have antibodies formed against both anti-A, both A and B, because A and B antigens are not present in the person having blood group O. From this, we of course understand the fact that O is the universal donor and AB is the universal acceptor. A can accept only from A or O, and B can accept only from B and O. That is basically looking at the fact that there could be rejection. Rejection, why? Because antibodies against the, so if a person having blood group A is given blood which is blood group B, then because the person already has anti-B, anti-B will bind to the B antigen and there will be hemagglutination. And so the blood that was given would be completely destroyed. So this is something that is very clearly understood. Now, what is another important facet is that suppose there is a person having blood group A, he or she generally already has an antibody against B. Now, the question that comes up over here is when this person does not have any antigen against, is not exposed to blood group B earlier or is not ever exposed to blood group B, then how is it that it already has anti-B? I hope you're getting what I'm trying to say. A person having blood group A may already have antibodies against B. So the question that comes up is, if this person has not been transfused with blood B, then how is it that it already has how is it that the person already has anti-B? So what has been observed over the years is that there are lots of microbes which have similar sugars on their surface. And so most of the people would have antibodies against those sugars that are present in the microbes. And because the sugar moieties are more or less similar, The antibodies that have been formed against a particular microbe can also cross react with the RBCs that are coming from the person who have blood group B. So therefore, the understanding is that the microbes may have the same sugars, and therefore the body may already have antibodies that can recognize the antigens present on the transfused blood. This is something that has been observed. Now, what are the clinical manifestations of ABO incompatibility? So, when we say ABO incompatibility, is just that a person having blood group A can never accept blood from a person having blood group B. Likewise, a person with blood group B can never accept blood from a person with blood group A. So, there is where you have incompatibility present. Now, suppose you have a transfusion, okay, wherein the blood groups have not been matched before the transfusion, then you can have clinical manifestations. So you would have immediate or delayed hemolysis. Hemolysis basically means the lysis of the RBCs, and that is because the antibodies bind to the surface of the RBCs, and that initiates either it mediates either complemented mediated destruction or antibody dependent cell cytotoxicity. So within few hours, what will be observed is hemoglobinuria, which means that hemoglobin will be seen in the urea. Because while filtration of the blood, all the hemoglobin that has been released into the blood because of the lysis of the RBC will all be filtered in the kidney, and therefore the hemoglobin will be released in the urea. Then again, what can happen is, because the HP is released from the lysed RBC, it can get converted to bilirubin, and we all know that accumulation of a high concentration of bilirubin can be very toxic, also leading to conditions like jaundice. So in certain cases, therefore, jaundice and anemia is a manifestation observed whenever there is ABO incompatibility. So what could be the treatment if there is a transfusion that has happened without matching the bloods, or because of some contamination in the blood? So the treatment generally that is used is give diuretics, and since diuretics are given, there is a lot of removal of removal of urine. So what happens is, slowly it will clear the free hemoglobin from the kidneys, and there is no accumulation of these hemoglobin because of the diuretic. So that is the treatment generally that is carried out. The second important example of type 2 hypersensitivity is what is called as hemolytic disease of the newborn, and it is also called as erythroblastosis fetalis. So as you can see, erythro stands for RBCs, blastosis, it means that there is a lysis, and fetalis is basically in the fetus. Now this occurs when an Rh negative mother uh, has in her womb Rh positive fetus developing. So when you say Rh negative mother, it means that the mother's RBCs do not have the Rh factor, while the fetus would have the Rh factor present on the surface of its RBCs. Now, how is this possible? It is possible because the father may be Rh positive, or father may have Rh positive. So then the fetus can have the Rh positive present. So you must understand that the Rh negative mother, because has never been exposed to Rh positive, initially will not have any antibodies against the Rh factor. Okay, but what has been observed is that during the first pregnancy, when the delivery is to happen and the placenta gets dissociated from the from the basic uterus, okay, so what is observed is that when you have the placenta getting a little dissociated during delivery, you can have blood of the infant passing through the placenta into the mother's blood. Now, therefore, when the RBCs of the fetus enters the blood of the mother system is going to recognize the Rh positive RBC as foreign, because it has an Rh antigen, while the mother cells do not have an Rh antigen. So, therefore, it will recognize this as non-self, and slowly, gradually, therefore, the mother will kind of have its B cells getting activated, differentiating into plasma cells, and these plasma cells will give rise to IgMs that can go and bind to the Rh specific, that can go and bind to the Rh specific RBC. In the process of differentiating, it also forms memory cells. So basically what we are trying to look at is, once exposed, the mother already has or remembers the Rh factor. And so you can say in a way the mother is already sensitized to the Rh factor. So if the next pregnancy is also such that the fetus has Rh positive, or it has Rh positive blood, that means has the Rh factor. Now this time on, because it has the Rh factor and the mother already has has a memory of the Rh factor, the moment you have the RBCs entering the blood system of the mother will give a very fast response because it already has a memory. So it has acquired memory, acquired immunity against the Rh factor. So in this case, what is going to happen? Antibodies that are produced by the plasma cells, that to IgG, which are very highly specific for Rh factor, would actually pass through the placenta and enter the fetus, and in the fetus it is going to bind to the Rh factor and destroy the destroy the RBCs of the child. So therefore the manifestation would be the child would be anemic. Now, in order to ensure that this does not happen, because one can monitor whether the child is Rh positive or not, that can be done by a simple Coombs test. So in Coombs test, what one does is that one takes the RBCs and then exposes it to anti-Rh, and when the anti-Rh binds to it, if there is lysis of the RBCs, that means the blood of the fetus contains RBCs that has Rh factor. So during pregnancy, blood from the fetus can be retrieved and Coombs test can be done to check whether the Rh factor is present or not. So that is how one can monitor, also monitor whether the Rh factor has entered the mother or not. Now, this because we know that during delivery there are more chances of the RBCs entering the mother's system. Therefore, before delivery itself or during delivery itself, the mother can be injected with ROGAM. ROGAM is basically an antibodies for Rh. So what happens is that if the mother has already antibodies against Rh, then that antibody will go and bind to the RBCs that are released from the placenta. So instead of the RBCs being taken up by the B cells and presented and then differentiated into plasma cells, the Rh is already bound to the RBCs and this would undergo lysis. So in the mother, the RBC of the infant is going to get lysed, but it is not going to be recognized, or it doesn't allow, or it doesn't give the time for the mother system, immune system, to recognize this as foreign and produce antibodies and memory cells against this. So this is in a way that you can have erythroblastosis fetalis getting prevented. So essentially, what is important to note is that by using ROGAM, one has been able to prevent abortion of, natural abortion of the fetus, because if you have the antibodies from the mother system enter the fetus, then the fetus can become so anemic because of the destruction of its RBCs that the fetus inside the womb can die, and therefore one can have abortion. So this is something that can be definitely prevented. Now we have another example, and that is drug-induced hemolytic anemia. So what has been observed is several drugs, like penicillin, etc., cephalosporin, etc., can bind, okay, to certain cellular proteins, and or it can also bind to the surface of RBCs. So when it binds to the surface of RBCs, what happens is that the RBCs become a target for the antibody that can bind to the drug. So therefore, you would have a lot of antibodies that can come and bind to the RBC itself, and this would induce complement mediated destruction of the RBCs per se, or it can also induce antibody directed cell cytotoxicity. So drugs like penicillin, cephalosporin are able to bind to the surface proteins on RBCs. So what happens effectively is that the drug plus the proteins will act as hapten plus carrier. So you essentially are looking at the fact that when the drug is binding to the RBC, it is acting as a hapten plus carrier. So it is entirely antigenic. And so it will induce antibody formation. And with the antibody formation, the antibody can come and bind to these RBCs. And then, of course, you can have destruction of the RBCs happening. So that is something that is important and has been observed in many drug related hemolysis. So effectively, generally there is complement activation, and because of that the person suffers from hemolytic anemia. So let us make the conclusions. Type 2 hypersensitivity is in response to an immune complex formed when antibody binds to an antigen on a cell. The target cell bound to by the antibody can be eliminated by complement system or by the antibody dependent cytotoxicity. The blood groups are antigens that on binding to an antibody can lead to ABO incompatibility, which in turn leads to hemolysis. RH incompatibility, that is the hemolytic disease of the newborn, and drug-induced hemolytic anemia are two other examples of type 2 hypersensitivity. Therefore, type 2 hypersensitivity is antibody-mediated cytotoxicity, leading to either immediate or late phase reaction, with the cytotoxicity enhanced once it is sensitized. So the first exposure definitely makes the person sensitized against that particular antigen, and therefore you would have a heightened response the second time on. Thank you.